In this lesson, we're going to take a look at implicit differentiation. What we've been doing so far has been explicit differentiation, which means we've only been doing differentiation with explicit equations or functions. So just as a quick recap of what is an explicit equation versus an implicit equation, an explicit equation is one that is written as a variable equals and an expression that does not include that variable. Includes other variables, but not that variable. So for example, y equals x plus 16. So it's written as y equals, and then on the other side, there are no y included at all. Or all your functions are going to be explicit equations. F of t equals t squared minus 3t. So we're saying f equals, and then there's no f's on the other side, it's only t's on the other side. Versus an implicit equation, which mixes more than one variable together. So we've got, hopefully you recognize this from your conic sections. Here's a circle. The equation of your circle is x squared plus y squared equals 16. And you would know this is the radius of the circle is 16 and it's centered at the origin. So that's just an example of an implicit equation where I mix x and y together. And implicit equations don't have to be functions. So in the case of a circle, it would fail the vertical line test. But that's fine. We don't have to have functions to do differentiation. We can actually do it on pretty much any equation. So we're going to look at how in the world would I take a derivative of an equation like x squared plus y squared equals 16 in this lesson. And that would be, remember, derivative is the slope of the tangent line. So if I'm thinking about a circle, any point, there's a tangent to the circle, and I could find the equation of the tangent line or just the slope of the tangent line. So let's remind ourselves a little bit about some differentiation of explicit and taking along with that the chain rule. So let's take a look at our first case, which is d by dx of just x. Now you know already right off the bat this is going to be 1. And the reason for that, if you like, is that we say this is a 1 here, and so the 1 comes down in front and I end up with x to the 0. And if I was thinking about this in terms of a chain rule, if this is the derivative of the outside, the 1 comes down, then the derivative of the inside would be dx dx. Well, this kind of looks like a fraction. Turns out this is just equal to 1, and this is just all going to be equal to 1. So again, what happens is the 1 comes down, I subtract from the exponent, so this becomes a 0, and I've got dx dx. This is again the derivative of my quote-unquote inside, or my x prime if you like, or my g prime, but it just turns out like a fraction. It's going to be equal to 1. When I do the same thing with y, thinking, okay, this is a y to the 1, and I'm taking the derivative with respect to x, then what's going to happen here is this ends up, again, the 1 comes down in front, I get y to the 0, and then my derivative of the inside is going to be a dy dx, or the derivative of y. You could also write this as y prime. And this just simplifies down to dy dx. It doesn't simplify down to 1 because the dy and dx, they don't cancel. They don't kind of simplify out. I do end up with just a dy dx. Think of this as the derivative of my inside of my original function. Okay, similarly, if I was going to do this again, this would be 2 comes down in front, I get an x to the 1, and then this would be like there was a dx dx written after it. Again, thinking chain rule, thinking derivative of your inside. Your inside is just the x itself. And we know this is going to simplify down to just be 2x. In the case of the derivative of y squared with respect to x, we're going to follow the same steps. The 2 comes down in front, I get a y to the 1, and derivative of the inside, well in this case my inside is a y, so this is going to be a dy dx. And that would be as simple as it gets. I mean, I could erase this 1 up here, I don't really need it, but this is the general idea. So in other words, whenever you take a derivative of something in terms of y with respect to x, we end up with this dy dx at the end as part of our chain rule, as part of our inside function, our g function inside. Okay, so d by dx of e to the 5x, well I know that would be e to the 5x is just itself, e to the 5x, times derivative of 5x, it's just going to be 5 times dx over dx which is going to simplify down to 5e to the 5x. Okay, same steps. I'm going to end up with e to the 5y. Derivative of 5y is going to be 5 times dy dx. And I could rearrange this if I wanted to be 5e to the 5y times dy dx. Okay, so the idea here is that before we didn't even bother to write this dx because it just kind of cancels out, goes away, goes to 0, and you hadn't learned the chain rule yet. When we take the derivative of y with respect to x, I end up with these dy dx's as part of my answer. Now, if I was taking the derivative of d by dy with respect to y, that would just be, well, dy over dy is going to be 1, just like dx over dx is equal to 1. But with the y, it has to depend very much on what you're taking it with respect to. And that's why Leibniz's notation is kind of handy in this case. So let's see how this fits in the scope of a more complicated example. So here we've got steps for implicit differentiation. We want to find dy dx, so we're actually going to solve for it. It's not going to pop out straight away. For y squared minus 5x cubed equals 3y. So step 1 is just to take the derivative of each term, and each time you take the derivative of y is involved, you have to include a dy dx after it. So again, starting with the derivative of y squared, the 2 comes down in front. I've got then still a y, and because I took the derivative of y, I'm going to write this as dy dx. Okay, then I subtract. This, again, does not involve y, so I'm not going to need the dy dx. I'm just going to use my straight-up power rule. So 3 comes down. 3 times 5 is 15. X to the 3 minus 1 is 2. And then on the other side, again, this is going to be a derivative with respect to y, so this is just going to be 3. And then I've got dy dx. Okay, so that's the first step. Everywhere that I've taken the derivative of y, here and here, I end up with a dy dx on both places. Once you've got that, step number 2 is gather all terms with dy dx on the left side. It can actually be on either side, whichever one you like. We just tend to like the left side because we're going to try to get it to be dy dx equals. And everything else should go to the right side. So in terms of dy dx, I've got this one, which is already on the left side. And I've got this one, which is on the right side. I'm going to subtract it over. So I'm going to leave this here, 2y dy dx minus 3 dy dx. Just treat dy dx like a variable. And then I need everything else on the right side, so I'm going to add, this has no dy dx's, I'm going to add it to the other side to get 15x squared on the right side. Move it over, basically swap these two. Okay, so once I've got all my dy dx's on one side, sometimes there's only one, and then it makes it easier. If there's 2, then you need the next step of factor out the dy dx if necessary. So these have a common factor of dy dx, so I can pull that out front. And then inside I'm left with, here I've got 2y, and here I've got minus 3 is 15x squared. And that creates me with one term with dy dx, and to get that dy dx by itself, I'm going to divide by this 2y minus 3. So I've got then dy dx equals 15x squared over 2y minus 3. So we have found dy dx using implicit differentiation. Now note that this has both x's and y's involved in it. So if I needed to find the equation of the tangent line, I would need to plug in a value for x and a value for y at any point on my curve. You could graph this if you wanted to see what it looks like. So in this case, I'd need both x and y, but I can do that. And remember, this is the slope of my tangent line at any given point on my curve. So take a minute to review those steps before you continue with the video. Think through again, step 1, 2, 3, 4, what do we actually do? And then pause your video and try example number 1 down below. Pause your video, try all the steps, and then come back and see how you did. So there it is. got the answer? Double check the ear steps all match up. Again, this is step 1, step 2, step 3, step 4. So it should be fairly straightforward to follow along and see how you did. Let's take a look at number 2, which is just a little bit more complicated. So what I've got on the left-hand side, is a chain rule. And inside I've got a product rule. So I'm going to start out with the chain rule part of it, which is going to be the derivative of sine is cosine. So I've got cosine of x times y times, again, now I need to take the derivative of the inside, which is this part here. And so I'm going to say f prime is 1 times y plus f times g prime. And in this case, you can write dy dx if you want, or you can also write that equivalently as just a y prime. If you like to save yourself a little bit of work, this is a little bit shorthand way of writing it. Just remember that you need to keep straight which are your y's and which are your y primes, and that this is a y prime, not a y to the 1. So if you want to take a little bit shortcut, not have to write dy dx all the time, you can write it as y prime. Just make sure you keep them all straight. And that is equal to, on the right hand side, I've just got a straight up power rule. This is just 10. Okay, and now my goal would be to solve for y prime. So in order to do that, I'm going to divide out the cos xy. So that just gives me y plus xy prime equals 10 over cos xy. And just to save myself a little bit of fractioning, I'm going to change this cos xy is actually going to be a secant xy if I bring it to the top. So this would be equivalent to 10 of secant xy using my reciprocal identity. So 1 over cos xy is secant, so since it's on the bottom, I can bring it to the top and make it a secant. Okay, then I'm going to try to solve this y prime, subtract the y to the other side. So I've got xy prime equals 10 secant xy minus y, and divide out the x to get y prime equals 10 secant xy minus y all over x. And I could write this again as dy dx equivalently. And if the question asked me for dy dx specifically, I probably should write my answer like that, with the dy dx instead of the y prime. So there you go. Chain rule, product rule, and implicit differentiation all at once. It's a mouthful, but you can do it one step at a time. Okay, so now we said you can find the equation of a tangent line even if what you have is not a function. So here we've got a circle, and it's asking us to find the equation of all tangent lines for x squared plus y squared equals 4 when x equals 1. So here is x equals 1, and on my circle, that would be a point about here, and a point about here. So I'm actually going to have 2 tangent lines. Let's see if we can actually just sketch those in. So that would be more or less what my tangent lines are going to look like at the point x equals 1. So I'm going to need to find both of those equations. Now, first off, I know my equation for a tangent line in general is y minus y1 equals mx minus x1. So in this case, I'm going to have to find these 2 points. I know the x value already for both of them is 1, but in order to find this y value that I'm going to plug in here, I need to solve for y in this equation. So I'm going to plug in the x value of 1, so I've got 1 squared plus y squared equals 4, and I'm going to solve for y in order to find my coordinate points. So this would be y squared equals 3, square root, y equals plus or minus square root of 3. And so this would be the point 1 positive square root of 3, and this would be the point 1 negative square root of 3. So again, when I'm thinking I'm going to use my point slope form, I'm going to have 2 different y1 values. Okay, so that gives me, again, the points to plug in for y1 and x1. Now I need to find the slope. And for the slope, I'm going to need to find the derivative. So I'm going to take the derivative of x squared plus y squared equals 4. That's going to be 2x plus 2y dy dx equals 4. Nope, not 4. That's a mistake that a lot of students also make. The derivative of a constant, remember, is always going to be 0. So handily, that just disappears. It's only 4 if it was 4x. So I'm prone to making these mistakes as well. You want to watch out. Derivative of a constant, 0. Okay, so I want to take this and solve it for dy dx. I'm going to subtract the 2x to the other side and that gives me 2y dy dx equals 2x. And divide out the 2y, the 2's are going to cancel, and this is going to give me just x over y. Sorry, I dropped a negative. Negative 2x, negative x over y. So to find, again, the slope of each of these tangent lines makes sense, is not going to be exactly the same. I need to plug in the values of x and y into my derivative. So let's call this line 1 and this line 2. So slope number 1 is going to be, m1 is going to be plug in, so it's negative x value of 1, y value of positive root 3. And if this is, so this is going to be m1 is negative 1 over root 3. It's a negative, that makes sense because we're going down to the right. And slope number 2 is negative 1 over negative root 3, which is just going to be 1 over root 3. So my m2 is going to be 1 over root 3. I'm going to handily move this off to the side so I have a little bit more space to write my actual final answers, if this is going to let me. Yes. Okay, so moving over just a little bit. Okay, so I'm going to use this equation to write the slope of each of these, write the equation of each of these tangent lines. So for number 1, my line number 1, y minus y1 is root 3, is equal to m is negative 1 over root 3, x minus x1, which is just 1. So there's one of my answers. And the second one is going to be y minus negative root 3, so plus root 3, is equal to, this time it's a positive slope, 1 over root 3, still x minus 1. That would be my second equation of the tangent line. And there it is. You're done. So again, a similar idea for how we found tangent lines with explicit differentiation. You need to be able to have a point to plug in, and you need to be able to find the slope, and you use the derivative in order to find the slope. It's just that. Now we're using implicit differentiation to find the derivative, and because our equation is not explicit, we're going to have to solve for y values for points. Okay, one more thing before you get set loose to work on your homework. Horizontal tangent lines and vertical tangent lines. We want to actually find these equations. So first we have to figure out where do they exist. Now horizontal tangent lines exist when your slope dy over dx equals 0. In the case of a fraction, this actually is going to end up meaning that the numerator is equal to 0. On the other hand, a vertical tangent line exists when the slope dy dx is undefined. So again, we're thinking, okay, horizontal line, flat, slope, vertical tangent line, vertical, infinite slope. In this case, in this lesson, we're going to say it's wherever it's undefined. In the case of fractions, again, this is going to mean your denominator is equal to 0. So there actually could be other reasons that your derivative is undefined if you had something like cusp. And at this point, we don't necessarily have a vertical tangent line. Our derivative is undefined. But for the purposes of this example, we're looking at, or for this lesson, we're looking at where your slope is undefined, particularly because the denominator is equal to 0. So let's take a look at an example. Number 4 says find all horizontal tangent lines of the graph 3x squared plus 2y squared equals 16. And number 5 is the same expression, just finding the vertical ones. So we want to find where the derivative is equal to 0. That's going to tell us where our tangent lines are, and then we've got to figure out what the actual equation is. So I'm going to take the derivative of this. So first one is just straight up power rule. 3 times the 2 is 6. X to the 1 plus 2 comes down, I've got 4y times dy dx. And that's equal to derivative of 16. Remember, constant is going to be 0. And to solve this, we need to solve this for dy dx. I'm going to subtract the 6x to the other side. So I've got 4y times dy dx is equal to negative 6x. And divide out the 4y. Gives me dy over dx equals negative. I'm going to simplify 6 over 4 is going to be 3x over 2y. And I need to figure out where this is equal to 0. And again, we said this is going to be equal to 0 if my numerator is equal to 0. So this is going to be then where this part is equal to 0. It's going to be, well, 3x is equal to 0 gives me x equal to 0. Now, this is where I have a horizontal tangent line. It is not yet the equation of my horizontal tangent line. This is the location, not the equation. If you think about a horizontal line, horizontal lines have the equation y equals something. That's what a horizontal line has the equation of. So I've got to plug in this x equals 0 into my original equation and solve for y to see what I get. So I've got 3 times 0 squared plus 2y squared equals 16. And if I solve that, divide out the 2 and square root, I get y equals plus or minus root 8. If you wanted to simplify this, you could make this plus or minus 2 root 2. If you want to give this as a decimal answer, that is also acceptable in this lesson. You can use your calculator to get decimal answers. So this would be the equation of my horizontal tangent line would be y equals plus or minus 2 root 2, y equals plus or minus root 8, or y equals whatever decimal this happens to give you. So again, I'm going to emphasize this. This x equals, this is the location, this is where I'm going to get a horizontal tangent line. And if you wanted to graph this on Desmos and see what your curve looks like, it should flatten out at this place, x equals 0, but this is the y value at which it flattens out. Okay, so number 5, find the vertical tangent lines of the graph. Again, I have the derivative already, so I've got dy dx equals negative 3x over 2y, and this is going to be undefined where my denominator equals 0. So where my 2y is equal to 0. So 2y equals 0 where y equals 0. And again, this is the location of my vertical tangent line. It is not the equation of the vertical tangent line. The vertical tangent line would have an equation of x equals something. So I need to find out what that is. Again, same way as I did before by plugging this 0 in for y and getting myself 3x squared plus 2 times 0 squared, 0, not 6, 0, is equal to 16, sorry. And solving this, I'm going to divide by 3 and square root. So I've got x equals plus or minus square root of 16 over 3. If you wanted to simplify this, this would be plus or minus 4 over root 3, or even one more step, plus or minus 4 root 3 over 3. Any of those would be acceptable as an answer, or your decimal answer would also be fine. And that's it for today's lesson. So again, use your derivatives to find horizontal and tangent lines by making the numerator or denominator equal to 0. If you don't have a denominator, if you don't have a fraction, then to find horizontal tangent lines, you just set your whole thing equal to 0. And if you don't have a fraction, then there's nowhere you're going to be undefined, so you don't have to worry about your denominator being equal to 0. All right, good luck with your homework.